Hi everyone, this is Mrs. GA, and today we're going to learn about limits at infinity and horizontal asymptotes. All right, here's a quick warm-up, so please pause the video and give it a try. All right, go ahead and check your work here. So for part A, we have two vertical asymptotes, which essentially can be found by setting your denominator equal to 0. And then our horizontal asymptote is at y equals 2. I'll review y in just a second, but hopefully you remember these rules. For part B, you can factor and simplify out. We do have a hole at x equals -4. Remember, that's that removable discontinuity that we've talked about. We have the vertical asymptote at x equals 4 and horizontal at y equals 2. Here you can factor the numerator to check for a removable discontinuity, but there are none. So you still have that vertical asymptote at x equals 5. And here we don't have a horizontal asymptote, but if you do a little bit of long division, you can find that there's a slant asymptote at y equals 2x plus 3. And then last here, factor the denominator to help you find the vertical asymptotes at x equals 1/2 and -2/3. And then in this case, the horizontal asymptote is at y equals 0. So just a quick recap of what we learned in pre-calculus about the 3 rules for horizontal asymptotes of rational functions. So if you had any questions about the warm-up, remember when you have a rational function that looks something like this, we're going to be comparing the degree of the numerator and denominator for these 3 cases. So if the degree of the numerator is less than the degree of the denominator, then we're going to have a horizontal asymptote at y equals 0. Essentially, our denominator is just growing much faster than our numerator, so our graph will just approach 0. If the degrees are equal, as in case 2, we're actually going to have a horizontal asymptote at the ratio of the leading coefficients, so see a over b. The general idea there is that everything essentially cancels out, and everything that's a lower degree essentially cancels each other out as we go towards positive or negative infinity, leaving us with just the a over b. And then if the numerator degree is more than the denominator degree, we will not have a horizontal asymptote, but if we might have a slant asymptote if m is exactly 1 more than n, as in part C of the warm-up, or we may have other oblique asymptotes if the degree is even larger. So these were the rules that we learned in pre-calculus. Again, we kind of just memorized these rules and use them. So today we're going to talk about limits at infinity. So limits at infinity are essentially describing horizontal asymptotes. So it's referring to the end behavior of our graph. So what's happening to y as x approaches positive or negative infinity. I do want to note that this is different than an infinite limit. Okay, so this is the limit as x approaches infinity. Or negative infinity. So again, we're really just looking at what's happening as x increases or decreases without bound. So here you kind of have 3 cases of what a horizontal asymptote might look like. I do want to point out horizontal asymptotes are not exactly the same as vertical asymptotes. Vertical asymptotes are actual restrictions in your domain. You cannot touch a vertical asymptote, you cannot cross a vertical asymptote. But horizontal asymptotes, again, kind of just describe where your graph is headed. So it's completely fine to cross over a horizontal asymptote, or maybe your graph won't cross it, just depends, but it is completely fine for your graph to cross a horizontal asymptote. But you'll just see as x approaches positive infinity, in all of these cases, our graph starts approaching that horizontal asymptote, which we can actually describe as a limit. So we say the line y equals L is a horizontal asymptote of f of x if the limit as x approaches positive or negative infinity of f of x equals L. So again, horizontal asymptotes are really just limits at infinity of our graph. So now we're going to learn how to evaluate these limits at infinity when we have different indeterminate scenarios. So if we are using direct substitution with a rational function to evaluate a limit, we are going to end up with some form of infinity over infinity, which is an indeterminate. Okay, so we need to know how to address this indeterminate. So remember, previously we worked with the indeterminate 0 over 0. Here we're going to work with some form of positive or negative infinity over positive or negative infinity. So when you see this case, the trick that we're going to use is going to be, we're going to divide the numerator and denominator by the highest power variable in the denominator. This should help us be able to then evaluate using direct substitution. We'll look at each individual term as x approaches that positive or negative infinity. A few things I want to note are not indeterminate. A number over infinity is not indeterminate. That scenario will approach 0. So this, if we ever see this scenario, we can evaluate that limit. It will be 0. And if you have plus or minus infinity over a number, that is also not indeterminate. We can evaluate this limit. This will approach positive or negative infinity. And I suppose I can add a plus or minus here as well. Either way, it will approach 0. So again, the case that we're really looking for is that infinity over infinity. That's when we divide the numerator and denominator by the highest power variable in the denominator. All right, so let's give this one a try. So again, if we just use direct substitution to try to evaluate this limit, if you plug it in here into the numerator, 2 times infinity squared plus 5 is just going to approach infinity. And same thing in our denominator, the denominator would approach infinity. So again, this is indeterminate. So we need to address it to find the actual limit. So remember, we're going to divide the numerator and denominator by the highest degree variable in your denominator, which is x squared. So we're going to find the limit as x approaches infinity of 2x squared over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. So we have to divide everything in the numerator and denominator by x squared. And simplifying that gives us the limit as x approaches infinity of 2 plus 5 over x squared over 3 plus 1 over x squared. So from here, we're essentially going to evaluate each individual part as x approaches infinity. So as x approaches infinity for 2, well, that's just going to remain 2. We're essentially doing direct substitution here. But as x approaches infinity here, we end up with 5 over infinity, which remember approaches 0 because we're taking 5, we're dividing it by a really large number that's going to approach 0. So this part essentially just approaches 0 as x approaches infinity. And then in our denominator, well, the 3 will still approach 3. And again, as x approaches infinity here, where we have 1 over infinity, which again approaches 0. So that just leaves us with the limit of 2 over 3, which does follow the rule that we learned in pre-calculus, the ratio of the leading coefficients. However, in calculus, we need to make sure we're doing it while following our properties of limits. All right, let's give this next one a try together. So again, if we just use direct substitution, we will end up with infinity over infinity, which again is that indeterminate. So we need to divide everything in the numerator and denominator by the largest degree of our denominator, which is x squared again. So we're going, and I'm going to do this while simplifying. So if I divide this term by x squared, we're just left with 2x, and then we have plus 5 over x squared. And then in our denominator, we would have 3 plus 1 over x squared. So now we can evaluate each individual part as x approaches infinity. So as x approaches infinity here, this will approach infinity. As x approaches infinity here in this term will approach 0. As x approaches infinity for the 3, this will approach 3. And as x approaches infinity here, again, this term will approach 0 because a number divided by infinity will approach 0. So if you look at the limit that we have, it's infinity over 3, which will just approach infinity. So this one, the limit as x approaches infinity of our function equals infinity, which means that our graph will essentially just keep increasing without bound as we move to the right. And again, this does follow the rules that we learned in pre-calculus. This one would actually follow a slant asymptote, but here our limit is simply positive infinity. All right, let's try this next one together. Again, direct substitution here would lead us with the limit infinity over infinity, which again is our indeterminate. So let's divide the numerator and denominator by x squared. So that leaves us with 2 over x plus 5 over x squared over 3 plus 1 over x squared. And now we're ready to evaluate the individual parts. So 2 over x as x approaches infinity will approach 0. 5 over x squared will approach 0, so our numerator will approach 0. And then in the denominator we have, this portion will approach 3, and this portion will approach 0. So we can see that the limit as x approaches infinity is simply just 0. And again, this does confirm the rule that we learned in pre-calculus when the degree in the denominator is larger than the degree in the numerator. So here, our limit as x approaches positive infinity is 0. All right, so let's look at this next example together. This one's a little bit trickier, so we'll walk through it slowly. So again, if we do direct substitution here, and again, this is the limit as x approaches negative infinity. If we do direct substitution, we end up with negative infinity over positive infinity, which is an indeterminate. So we need to do a little bit of extra work here. So when you see a radical in part of your rational function, if there's any way that we can try to simplify it or rewrite it, we will. So you'll notice here that we actually have the square root of an x squared term. So we're going to want to try to simplify part of that variable out. And we can actually do this by within your square root, we can actually factor out x squared. And that does leave us with 4 over x squared plus 1. Again, this is all within our radical. And then here, as I gave you guys a little hint, if you have the nth root of x to the power of n, it will equal the absolute value of x. Remember, we need to make sure that our result is positive. Even if maybe the variable is negative, we can achieve that with the absolute value. So here, if we simplify this a little bit more, we get x over, and again, I'm just simplifying this portion of my radical, so absolute value of x times the square root of 4 over x squared plus 1. Now here's the part that becomes a little bit tricky. We need to remember that the function absolute value of x actually can be written as a piecewise function. So it's positive x for when x is greater than 0. It's actually negative x when x is less than or equal to 0. Remember, it can be written as a piecewise function with 2 linear portions. So if we're evaluating the limit as x approaches negative infinity, we're going to be working with this portion of our piecewise function. Again, it's because it's as x approaches negative infinity. So for this particular limit, we'll just say that the absolute value of x is just negative x. Again, it's this portion of our function. So we can actually rewrite this limit as the limit as x approaches negative infinity of x over negative x times the square root of 4 over x squared plus 1. And then here you can see that we can simplify. So this becomes the limit as x approaches negative infinity. I'll just say negative 1 over the square root of 4 over x squared plus 1. So I just moved the negative up to the numerator after simplifying out x. So from here, we can try again to evaluate this limit using direct substitution. So if you look at the numerator, we're left with negative 1. As x approaches negative infinity, this portion, 4 over x squared, this will approach 0. And then you're left with the square root of 1, which is 1. So we can see here that this limit as x approaches negative infinity is actually negative 1. So this is definitely a trickier problem, but it's important to kind of take note of some of these little strategies that we can use to help us try to rewrite our function to help us avoid that indeterminate form. So again, we try to simplify out the radical in any way we can. So we can simplify the square root of x squared to equal absolute value of x. And then the tricky step was, since we're finding the limit as x approaches negative infinity, we will just use this portion of our piecewise function. All right, so I have one for you to try on your own. So please pause the video and hit play when you're ready to check. All right, go ahead and check your work. I started by dividing the numerator and denominator by x squared, and then I evaluated the individual limits as x approaches infinity. So this portion will approach negative infinity, this portion approaches 0, this portion approaches 2, and this portion approaches 0. And remember, positive or negative infinity over any number will approach positive or negative infinity. So our limit is negative infinity. All right, I have one more for you to try on your own. So again, pause the video and give it a shot. All right, this one is definitely a more challenging one. So direct substitution gives us with infinity over negative infinity, which is indeterminate. So we can try to simplify a little bit and rewrite. So you'll see here that I factored out x to the fourth out of this binomial inside my radican. So I was able to simplify square root of x to the fourth, which would be the absolute value of x squared, which we actually don't need the absolute value signs because since we're squaring x, the result will always be positive. So this can just simply simplify to x squared. And then that leaves us with something that would still give us an indeterminate. So we can try dividing the numerator and denominator by x squared, which I showed this step here. So this actually will simplify to just 1. And that leaves us with our radical. And here we get 2 over x squared minus 1. So this limit we can evaluate. So as x approaches negative infinity, this portion will approach 0 and this portion will approach 0. And then the rest will approach the square root of 4 over negative 1, which is simply negative 2. So again, this kind of uses a couple tricks that we learned from the previous examples. So next we're going to look at kind of an interesting case of some functions that actually can have more than one horizontal asymptote. So let's look at the function f of x equals x plus 1 over the square root of x squared. So if we want to find all of the horizontal asymptotes, we'll want the limit as x approaches positive or negative infinity. So I want to remind you guys that the square root of x squared is equal to absolute value of x. So if we're looking at our function, we have x plus 1 over the absolute value of x, which we can write as a piecewise function. So we have x plus 1 over positive x when x is greater than 0. And then we have x plus 1 over negative x when x is less than or equal to 0. So here you can see that we just rewrote the absolute value portion as that piecewise of two linear functions. So we're actually going to have a different limit as x approaches positive infinity than when x approaches negative infinity. So let's start when x approaches positive infinity. So since x is approaching positive infinity, that's when x is greater than 0. So we would use this portion of our piecewise function. So it would be this. And if you evaluate this limit, we end up with that indeterminate form. So let's try, again, dividing the numerator and denominator by x. So we'll find the limit as x approaches infinity of 1 plus 1 over x over 1. So this portion will approach 0 as x approaches positive infinity, and that leaves us with the limit equaling 1 over 1, which is just 1. So we do have a horizontal asymptote at y equals 1. That's the horizontal asymptote as our graph moves to the right. But let's see what's happening as x approaches negative infinity. Let's see if we get something different. So since x is less than 0 for this limit, we're actually going to use this portion of our piecewise function. So using direct substitution here would give us the indeterminate negative infinity over positive infinity. So let's try dividing the numerator and denominator by x. So that would leave us with 1 plus 1 over x over negative 1. So as x approaches negative infinity, this portion of our function will approach 0, and you can see that we're just left with 1 over negative 1, which is negative 1. So this horizontal asymptote would be at y equals negative 1. So we actually have two different horizontal asymptotes for this function. All right, so I have one for you to try on your own. So again, please pause the video and give it a shot. All right, go ahead and check your work here. So remember, this function can be written as the piecewise function that you see here. So as we find the limit as x approaches positive infinity, we use this top portion of our function. We do need to divide the numerator and denominator by x, and then this would give us the limit of 5. So we have a horizontal asymptote at y equals 5. And then as x approaches negative infinity, we would use this portion of our function. Again, we get the indeterminate, so we need to divide the numerator and denominator by x, and then we can evaluate the limit, and that will actually approach negative 5. So we have a horizontal asymptote also at y equals negative 5. All right, so there is another indeterminate form that I want to talk about that you will see when we're evaluating limits at infinity. So that's the form of infinity minus infinity. So I know it may be your instinct to say, oh, infinity minus infinity is just 0. But remember, infinity is not an actual number. This is not the same as saying 5 minus 5. So this would be considered indeterminate because we don't really know if the function is headed towards infinity at the same rate for these different portions. So we can't really say that this infinity is the same as this infinity, so we can't just assume that it's equal to 0. So again, infinity minus infinity is considered an indeterminate. So we can address this in a couple of different ways. We can try factoring out the largest degree of our function, and then from there we can try evaluating the individual portions using direct substitution. Or we could also try multiplying by the conjugate. Just remember, you do need to do this in the numerator and denominator of your function. A few things that are not indeterminate. So infinity plus infinity is actually not indeterminate. If you ever have this scenario, your function will approach infinity. Or if you had negative infinity minus infinity, your graph would approach negative infinity. So this is not indeterminate. And neither is infinity times infinity. So this will approach positive infinity. Or if you have a negative in there, it will approach negative infinity. So really the main one to worry about is infinity minus infinity. Because remember, not all infinities can be considered to be the same value because they are not an actual value. All right, so let's give this one a try together. So here, if we use direct substitution to evaluate this, this portion of our function will approach infinity. And this portion will also approach infinity. So we're left with infinity minus infinity, which again is an indeterminate. So we need to try some strategy to rewrite it. And in this case, a good strategy to try, just because we have that radical, would actually be multiplying by the conjugate. Just remember here, so our conjugate will be square root of x plus 1 plus x, but we can't just multiply a numerator. We actually need to multiply the denominator, which is just 1, by the same thing. So don't forget. And then when we do that, if we simplify the numerator a little bit, this radical times this radical just gives us x squared plus 1. The next two steps would cancel out, and then what we have left here would be minus x squared. Okay, and then if we simplify our numerator, what we have left is simply 1 over the square root of x squared plus 1 plus x. So now we can try evaluating this limit. So our numerator will just keep approaching 1. If you substitute infinity here, this portion of our denominator will approach positive infinity. This portion will approach positive infinity. And remember, infinity plus infinity will approach infinity. And then if you have the limit 1 over infinity, this will always approach 0. Because again, you're taking a number and you're dividing it by a really, 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 really large value that will always approach 0. So this limit is 0. Again, I know it feels strange to multiply by a conjugate when you don't even see a fraction, but when we use this strategy, it did allow us to find the limit. All right, let's try one more together. So again, here, if we use direct substitution, we end up with infinity minus infinity, which is an indeterminate. So we need to find some way to rewrite our function so we can actually find that limit. So remember, another strategy you said might work. It seems a little bit, it's kind of a strange strategy, but it's factoring out the largest degree of our variable, which in this case would be x cubed. So if we factor out x cubed, again, that's just dividing each term by x cubed, we're left with 1 over x minus 1 as the remaining factor. So then this we can look at and we can try to evaluate it. So this portion of our limit will approach positive infinity. For this portion, well, this will approach 0, and then we have the minus 1. So our limit here ends up being negative infinity. So again, this is just kind of a strategy that you need to know you have in your toolkit that you can try when you have this indeterminate form. So the last thing I want to do is look at the limits at infinity for our arctan function. So I'm wondering if we can kind of use our knowledge of what we know about arctangent to help us find these two limits as x approaches positive and negative infinity, which would essentially be the horizontal asymptotes of these graphs. So first, it may help to do like a really quick review of what our tangent function looks like. So this is tangent of x. So remember, for a tangent of x for one period of it, we have vertical asymptotes at x equals pi over 2 and x equals negative pi over 2, and our graph looks something like this. With a couple key points that might be useful for us, we have pi over 4, 1, 0, 0, and then negative pi over 4, negative 1. So remember, for our inverse functions, really the domain and range are really flipped. And for this, we would restrict our domain of our original function to between negative pi over 2 and pi over 2. And that will allow our inverse function to also be a function. So if the domain is restricted here, the domain is restricted to negative pi over 2 and pi over 2, that means that the range of our inverse function becomes that. Remember, for inverse functions, domain and range is flipped. So since that would be our domain, that's our range, that means that we have something like this. So here's y equals negative pi over 2 and y equals pi over 2. And here our range is all real numbers. So that becomes the domain of our inverse function, negative infinity to positive infinity. And then we can also just take some of these values from our original function and swap the x and y. So instead of negative pi over 4, negative 1, we would have the value negative 1, negative pi over 4. So we can kind of just estimate that, 0, 0, and then we'd have 1 pi over 4. So we end up with a graph that looks like this. And it will follow along those asymptotes. So we do have those horizontal asymptotes, which would define our limits. So the limit as x approaches positive infinity of the arctangent of x would equal pi over 2, and the limit as x approaches negative infinity of the arctangent of x would equal negative pi over 2. So that's just a little review, tying stuff back to some of our trigonometric functions. All right, so that is all for today's video. Thank you so much for watching.